All right, hi, ladies and gentlemen. Welcome to our next lesson in Algebra 2. So last week, you guys were doing presentations on linear systems and how to solve them. And this week, what we're going to be talking about is multivariable linear systems. So basically taking a Algebra 2 twist on what you've already learned in Algebra 1. So you're used to doing elimination and substitution and solving a two-equation system with two variables. Well, what we're going to see this week is three variable systems that have three equations and how we can go ahead and solve those. So, well, the main thing we're going to be looking for is this thing called back substitution. That's kind of our main goal. If we can get our system to look like back substitution, we actually have a really easy time solving, because what we can do is just kind of substitute right up the line and solve for all our variables. So if you look here, we have z equals 2, y plus 3z equals 5, and x minus 2y plus 3z equals 9. Now, since I know that z equals 2, I can actually go ahead and do substitution and put that in for z in this equation right here. So really what I can say is that y plus 3 times 2 is going to equal 5. Well, because I have this equation, here's one variable, one unknown in my equation, this is really easy to solve for y. I can go ahead and multiply these and get 6, subtract from both sides, and I'll end up with y equals -1. I can then finish solving this by taking both these variables and plugging them into the top equation to solve for what x is. So if I go ahead and plug these in, I know z is 2, y is -1. I get that x minus 2 times -1 plus 3 times 2 equals 9. And then I can go ahead and solve this for my missing variable that I have here. So if we go ahead and we solve this, we have -2 times -1 is going to be a +2, so we'll have x plus 2. I have a 3 times 2 over here, and 3 times 2 is going to be 6, so we have plus 6, and that's going to equal 9. And then if I go ahead and I solve this, I know that 2 plus 6 is 8, and I can subtract that from both sides and get that x equals 1. So what you can see here is that this system has three different variables we have to solve for. We need to solve for x, y, and z. The ones that you looked at last week, you only need to solve for usually an x and a y or whatever your two variables were, but there were two you had to solve for. Here we have three variables and three equations, as I stated earlier. So my answer I have is 1, -1, and 2. X equals 1, y is -1, and z equals 2. Now, if you remember from last week, in your presentations, you showed graphing as well as elimination and substitution. And what's cool about that is that when we're talking about a two-variable, two-equation solution, we're talking about a point where your two lines touch. And that's actually also what we're talking about here. But you might say, but Mr. Guy, how can I write a point? There's three different numbers here. We're actually going to be talking about lines in 3D space. It's actually where these come from. There's three different variables showing us the 3D space of where these lines intersect. So if you can kind of think of in space, where are these lines crossing each other, where are they touching, there's three different things that are going to account for that. So the way we show this point is actually by writing it in terms of the order of x, y, and then z. So it's kind of like left, right, and up and down is kind of what we're looking at. So the x is going to be 1, my y value was -1, and then my z value was 2, and that's my final answer. Again, back substitution is really easy. You're probably watching this going, Mr. Guy, that makes a lot of sense. I have z equals 2. I put that in here. I solve. I put those both in here. I solve. Easy peasy lemon squeezy. The problem is that a lot of the systems that we're going to end up looking at are not in back substitution form. We want to make them look like that, and that's what makes it easy. So a guy named Gauss, which you might recognize that name from somebody we talked about previously, came up with a way in order to basically do elimination to get it down to look like something you can back substitute. So he called what he calls the row operations, things you're allowed to do in order to simplify your equation and make it back substitution worthy. Here are the three rules that you're allowed to do. You're allowed to interchange two equations, so I can flip-flop the order of two equations and move them around that way. You're allowed to multiply one of the equations by a non-zero constant. So I can say, hey, I'm going to multiply this whole equation by 5. When you guys did elimination, you did that a lot, right? Oh, these two things don't match up in order for me to cancel them out. So I'll multiply one by -2 or multiply it by 3 or whatever, and now they can line up to cancel. That was actually a row operation. You multiply a whole equation by a number. And then last but not least, you can add a multiple of one of the equations to the other. I can say, hey, I'm going to add row 1 and row 2 together and get this equation I'm looking for. And again, you did that when you did elimination with two equations, right? Okay, I multiply these and now line up, and now I'm going to do row 1 plus row 2, add these two equations together, and get a new equation, okay? Again, we are going to be using these operations to turn the system into a back substitution system. Back substitution, and then we can easily go ahead and solve, okay? So that's kind of our goal. All right, so what does that look like? What do we have to do here, Mr. Guy? I'm confused. Well, basically our goal is so that we create a system here so that the top equation only has all three variables, the second equation has two variables, and the last equation has one variable. If you go back and look at this example right here, notice my bottom equation has one variable, z, my next equation is y and z, and the top one is x, y, and z. We want this to look the same, x, y, z, or XYZ, XYX, or something like that, where we're kind of losing a variable as we go down. Now, we're kind of in a nice situation here where if we look, we actually already are missing a variable here, but we'll see where that comes into play a little bit later. The first thing I want to do is I want to identify what variable is going to be easy for me to cancel out, sort of like elimination, where we look at the x and y and say which one can I cancel easily. And what I'm actually noticing is that my x's are going to cancel pretty easily. I have an x, a negative x, and a 2x. Those all kind of look like they would cancel nicely because it's pretty easy to add multiples and make them go away. So the way that I show this is I say, all right, I'm going to be doing row 1 plus row 2. Row 1 plus row 2. And what I'm going to do is I'm going to do that into my second row to make this x variable disappear, and then go down and try to make this one disappear. So over here, I'm going to rewrite my top equation. I'm not going to do anything to touch that one yet. So 2y equals 9. I'm then going to go ahead and add these two rows together and replace this row with that addition. That's one of those row operations I'm allowed to do. So x and negative x is going to make that disappear. 2y and 3y will, or negative 2y and 3y will give me y. And then 3z and nothing will just be plus 3z. And then 9 and negative 4 will equal 5. Now, in this bottom row, I also want my x to go away. And if I look, I have an x and a 2x. So I want to think about with elimination, well, how would I make it so that those two will cancel? Well, the way that I'll do that is I'll multiply the top row by negative 2. And then the negative 2 times the top row plus the third row will make it so that that will cancel out. So if I do that, negative 2 times x will be negative 2x plus 2x will make that disappear. Negative 2y times negative 2 will be 4y plus negative 5y will end up being negative y. And again, I'm getting that because negative 2 times negative 2 is 4, plus negative 5 will be negative 1. Negative 2 times 3 will be negative 6, plus 5 will be minus z. And then last but not least, we'll have negative 18 plus 17, which will equal negative 1. So again, where did I get those numbers from? I multiplied that top row by negative 2. I then added it to this bottom row to make that x cancel out. And now I'm almost at the point where I have that back substitution. I almost have one variable, two variables, three variables. I just need to get rid of one of the ones down here. And what I'm going to be using is I'm going to be using the second row to make something disappear from the third row. If you ever have a row that has more variables than another one, you don't want to use it to eliminate with. Otherwise, you're going to have new variables re-show back up. So for example, if I said, hey, I want to get rid of this z, I have 3z and 3z, and I try to subtract those, I'm going to have a problem because what's going to happen is that these z's might cancel, but then an x will reappear because I have 0x sitting here. Remember, it's like 0 there. So what I want to do is I want to only make sure I'm using these next two rows in order to cancel something out. And luckily I have something that'll easily cancel these y's right here. So I'm going to be doing y and negative y and making those cancel. So I'm going to have this top equation stay exactly the same. I'm not going to do anything to it. I'm going to leave it. We'll solve for it when we do our back substitution. I'm also going to leave the second equation the same. I'm not going to touch it. But the third equation, I want to get rid of one of those variables. And the way that I'm going to do that is by adding row 2 and row 3 together. So I'm going to say, all right, row 2 plus row 3. because y plus negative y will make that cancel out and go away. 3z and negative z, if I add those together, will equal 2z. And then 5 and negative 1 will equal 4. I now have what we would call a back substitution system. I can easily solve for z, plug it in here, solve for y, plug this both up here, and solve for x. If I go and do that over here, I divide by 2, and I'm going to get that z equals 2. There's one answer. I then plug that in here, so then I'll have y plus 3 times 2 equals 5, so y will equal negative 1. Last but not least, we'll go ahead and solve for x. We'll plug both of these in the top here. So we'll have x minus 2 times 2 plus 3 times... Oh, actually, you know what? I'm putting the wrong thing in the wrong spot here. This guy's making a mistake. I want to make sure I put my y in for y and my z in for z. That could really mess up our answer if we don't put this in the right spot. And then we can go ahead and do this. So negative 2 times 2 will be 2. So we'll get x plus 2. And then 3 plus times 2 will be 6. So x plus 2 plus 6 has to equal 9. And then 2 plus 6 is 8. Subtract 8 from both sides. We'll get that x equals 1. And so my final answer would be 1, negative 1, 2. I always list them in the order x, y, z. And that is the point in 3D space where these three lines would be touching each other. Okay, that's an example of using row operations in order to set up this elimination, do this back row substitution. Okay. All right, so this is going to be the main kind of focus of this whole week for you guys, is doing these sorts of problems. We're going to have some example problems for you guys to try out. There'll be some work that I have assigned for you guys to do, but really come back and watch this example again if you ever get stuck about what to do. I gave a couple different words of advice. I'll also try to, I'll have another video uploaded here with another example just to show you another way that this looks. All right, thank you for watching. I hope you enjoyed.